Okay, so let's begin. Last time when we met, we introduced the concept of work, energy, and power. We looked at what work is, and we defined work based on the formula force times distance. The key highlight here being that the force and the distance must be parallel to each other for work to be done. And we also sought to say that if the force was to be at an angle to the direction of the distance, let's say the distance was horizontal, it became necessary for us to get a component of the force which should be parallel to that distance. So if this is F and the angle here was theta, we saw that the force that actually does work had to be F cos theta. And we also sought to say that it's actually possible to calculate work done by just evaluating the change in energy. So the change in energy can be used to evaluate what work done is. If something is being lifted upwards without accelerating it or at constant velocity, we sought to say that in that case, the work done was just the same as the change in potential energy. But this is if it is moving vertically upwards without accelerating. And we also saw that if something is moving on a level surface where the height is not changing, but the velocity is changing, then work done in that case can be calculated by just evaluating the change in kinetic energy. We'll look at a combination of these two in this session. So we have a few cases here. One to look at the work done by friction and what really happens there. And then apart from that, we also want to look at, so we have work done by frictional forces. Apart from that, we also want to look at the conservation of energy. Perhaps this is going to be the highlight of tonight's class, the conservation of energy. Then lastly, I think if we'll have time, we'll also touch on power. But here also, we'll also touch on the idea of non-conservative forces. So look at what non-conservative forces are, and also what conservative forces are. So for the last one, this is just going to be a brief description of what these concepts are. We might not really go deep into what those are. And if we'll have time, then we're going to conclude by defining what power is and how to actually work out problems that relate to power. So this is what we have for tonight. We're going to go, I think, for about an hour, hopefully. So you guys are free to ask questions if you are behind. Before we touch on what friction is, let us start with looking at the conservation of energy. We sought to say that energy comes in different forms. And for this unit, we agreed to say that we're just going to focus on the mechanical forms of energy, that is potential energy and kinetic energy. And to be specific, we agreed to say that we're going to focus on gravitational potential energy. So for the rest of this, when I write potential energy like this, I mean gravitational potential energy, even though I don't put that G there. So we're going to focus on gravitational potential energy and kinetic energy. Now, the conservation of energy just says one thing. If you have a system and you measure the energy that it has initially, so you measure the potential energy it has initially, you also measure the kinetic energy it has at the beginning, and then you compare with the potential energy it has afterwards, after some process, and the kinetic energy it also has after some process. The conservation says that at any particular point in time, the sum of the energy you started with will always be the same as the sum of the energy that you end up with. That is the conservation of energy in simple terms. Or you can say the potential energy initial plus the kinetic energy initial. This has to be equal to the potential energy final plus the kinetic energy final. So this is what the conservation of energy actually gives us. But originally stated, it actually talks about how energy is changing. So if a system is just observed, like you have a closed system that you are observing, meaning the conservation will say that we don't expect energy to really be lost, or we can't really create energy. We can't bring energy from nowhere. Whenever we get some form of energy, then it's coming from somewhere. So in general, it actually says if you calculated how potential energy is changing, and also calculated how kinetic energy is changing, add these two, what you expect to get is 0. So the conservation of energy. Okay, so yeah, we have a question. We have a question.
Sir,
It's a what?
are you able to hear me?
Yes, I can.
Then a question about everybody else. I can't hear a single. It keeps breaking the words phone. I can't hear anything.
Okay, Nancy is having trouble getting me. How about Joyce? Are you able to hear me just fine?
Yes, but I can't see the screen.
Whoa. For the screen, I am able to see it on my second device, which means it should be okay. So Nancy, it might be your network which is affecting, which is causing that.
I'm able to get you.
Okay. Yeah, so I have a second device connected. So if I can't see my screen on the second device, then it means that you guys most likely can't see it as well. But right now I am able to see it. And if I was to unmute, I would also be able to get myself. So meaning the audio, everything should be okay. Okay, so this is generally what the conservation of energy tells us. Now, if you look at this equation and this equation, they are actually one and the same. So we can choose to use either this version or this version. For the most part, we'll be using this version for our calculation. So for the most part, we'll be using this version of the conservation of energy for our calculations. But whenever it will be necessary, we'll still come back and touch on this version of the conservation of energy. Now, I have to just point out here, I'm reluctant to mention it because it's something that we haven't yet touched on. That is the issue of non-conservative forces. I have to say that this version of the conservation of energy, this is only if you are dealing with a case where you do not have non-conservative forces. So this is if non-conservative forces are not present. So if non-conservative forces are not present, non-conservative forces are not present. Then we're going to use this version of the conservation of energy. After we touch on what conservative forces and non-conservative forces, what they are, then we're going to introduce more like a corrected version of the conservation of energy, which also accounts for the presence of non-conservative forces. To give you an idea what non-conservative forces are, a very good example of a non-conservative force is friction. So friction is a very good example of a non-conservative force. So if friction is absent, and for the most part, you guys will only deal with friction as a non-conservative force. So if a question specifies that friction is not present, then this equation can be used. If friction is present, we'll look at a different form of the conservation of energy that you can actually use. That is after we define what a non-conservative force is. So back to this. This is what the conservation of energy states when non-conservative forces are not present. But how do you actually use an expression like this one? Well, let's look at a few examples. And to start with, we have this example here. Let's look at down a rough. So this is rough here. Rough means friction is present. So I don't really want to deal with this one. A block of mass M slides on a frictionless. Yes, this is going to work. So let's just get a diagram for this question so that we can easily relate to it. So consider an example like this one. where they're saying that we have a block of mass M, 5 kgs, that is released from rest from a point A and slides on a frictionless track shown in the diagram. So when you look at this question, they are saying frictionless, meaning that we do not have non-conservative forces here. So meaning if we have to use the conservation of energy, then we can just stick to PE initial plus KE initial is equals to PE final plus KE final. But let's finish going through the question. Let's see what we have. Let's see how we actually even decide that this is what works. Okay, so we have the mass given. We know mass plays a very big part in terms of the conservation of energy, even though sometimes it cancels out. So this object is released from rest from point A. Point A is here. What happens? It slides on a frictionless track shown in the diagram. So I'm saying that this track here is actually frictionless, meaning there's no friction. What else? Frictionless track shown in the diagram. Determine A, the block speed at points B and C. So we want to find the speed of the block when it reaches point B and also when it reaches point C. Well, how does it work? How do you know that conservation of energy works? Well, in the absence of friction, you decide or you determine that conservation of energy works if you're given the height from where you're starting from. If you know the height from where you're starting from, even without knowing the mass, you can determine the speed at any point. Even if I was to drop something from some height, and I say, I drop this object from a height above the ground, and I say 100 meters. And I say this object, it's starting from rest, meaning I'm dropping it. If I said non-conservative forces like friction, air resistance are not present, then I should be able to determine the speed of this object at any point using the conservation of energy. You guys looked at how this would be free fall, you know. So you should be able to use equations of motion to find the speed at any point. But even conservation of energy can work. Consider what the velocity will be by the time it hits the ground. Using conservation of energy, you'd say that, okay, if this is where you have PE initial and KE initial, then PE final will have to be here and KE final have to be at the bottom. According to the conservation, you have PE initial plus KE initial equals to PE final plus KE final. And if you substitute what these are, and notice that in this case, I haven't even mentioned what the mass is. I've only said from what height this object is falling. So if I choose the mass to just be M, you see that this is mgh initial for the potential energy plus half mv squared initial for the kinetic energy equals to mgh final for the potential final plus half mv final squared. Now, in this case, if the object is released from rest, what you should get from that is that its initial velocity was 0. It wasn't moving when you just released it. This tells us that V initial was actually 0, meaning the kinetic energy initial has to be 0. That's the first thing. Next thing, if I wanted to find the velocity at the bottom, meaning at the ground, when the height, where it has to fall all the way down, you have to see that the height final then must be 0. If I was to say the height initial at the topmost point is 100 meters. So this thing is falling. If the height final is 0, it's telling me that the potential energy final will have to be 0 because potential depends on height. This now implies that my equation reduces to just this. And if you look at this expression, the mass can now cancel from both sides of my equation, leaving me only with gravity 9.8, the height initial, which I took as 100, and then this to be half the velocity final, meaning the velocity at the bottom squared. From here, you see that it's actually easy to get what the velocity final will be. Because when I cross multiply the two, I'll have 2 by 9.8 by 100 equals to V final squared. So at the velocity at the bottom will be given by the square root of 2 by 9.8 by 100. This is what will give you the velocity at the bottom. Now here I just wanted to demonstrate that provided you know the height, you can find the velocity of an object at any point. Here it works the same. If friction was present between the slide and the box, the treatment would have been different. But because they're saying this slide is frictionless, it means that it's the same where we treated this object here, implying that even for our case here, all we have to ask ourselves is that, okay, this object starts from point A. At point A, what was its potential energy? So I will say PE initial, I'll just say potential energy at A. And then I'll say KE at A as well. These will be my initials. So my conservation of energy will be PE at A plus KE at A has to be equals to, let's say I wanted to find at point B there. All right, so in this case, it will mean that it will be the potential energy at B plus the kinetic energy at B. But what are they saying? If I was to bring this, I have mgh at A plus half mv at A squared equals to mgh at B plus half mv at B squared. So now comes where you get, is it falling from rest? Does it have an initial speed? The question says released from rest at point A. If it is released from rest at point A, it means that the velocity it had at A was actually 0. So V at A is actually equals to 0. The kinetic energy depends on that V at A. So this term has to be 0. So kinetic energy falls out from that expression. Now I have mgh at A equals to mgh at B plus half mv at B squared. This is what we have. When you reach this stage now, it's a little bit up to you again. There are two ways you can treat this question. The easiest way perhaps being just taking what the heights are. So what is the height at point A? If we go through the question or just looking at the diagram, you see that the height of the box when it is at point A is 5 meters or 5.00 meters. The height at point B is given as 3.2 meters. The height at C is given as 2 meters. So here now we can come back to our question. The height at A, first, before I even go to the heights, notice that the mass is present on each term. For me to do this, it has to be present on all my terms here, which you see is the case. So my mass can cancel out, leaving me only with GH at A equals to GH at B plus half V at B squared. From here, you can simplify this now by just making the substitution, or I can make VB since that's what I'm looking for. This becomes G H at A minus G H at B is equals to half V at B squared. Cross multiply that 2 so that I have 2 multiplying G at A minus G at B is equals to VB squared, so that in the end, VB will be equals to the square root of 2G H at A minus G H at B. This is what will give me the velocity at B. We can do the math. This is the square root of 2, G is 9.8 times H at A. At A, the height is 5. So at A, the height is 5. So I have by 5 minus 9.8 times 3.2 at B, and then get the square root of this. So can you try this? What are you finding? Someone try this one out very quickly. What are you getting? I think this should give you 5 point. This should give you 5.94. Yeah, this is what you should get. Okay, so we now have the velocity at B. Now, the question wanted the velocity at B and the velocity at C. You can try to do the same thing. For the velocity at C, you can choose. You can say PE at A plus P plus KE at B at S2. This has to be equals to PE at C plus KE at C. So again, mg h at A plus half mv at C squared. This is sorry, at A equal to mg h at C plus half mv at C squared. Again, the velocity at A is 0. This term falls out. The mass also cancels out. You end up with something like this. In the same way, you want to find what V at C is. So this is going to be GH at A minus GH at C equals to half. Sorry, the mass is not there here. We canceled out the masses. So this is V at C squared. Cross multiply that 2, we get 2 again. GH at A minus GH at C equals to VC squared. So that the velocity at C will now be equals to the square root of 2 GH at A minus GH at C. So you can try to do this and you should be able to get the expected answer. Okay, so I worked through this a little bit quicker because it's the same approach to how we found the velocity at B. Any questions on this? Regan, go ahead. Hi, Regan. You have your hand up. Regan, you have your hand up.
Oh, yes, sir. The second question, well, it says we need to find the final velocity at C. Why can't we use the B as our initial? Can it be the same?
Yes, it can still be the same. Yes, it can also work. So if you wanted to use that, right, of course, it would have to just be PE at B plus KE at B is equals to PE at C plus KE at C. This can also work. The only thing is, I wanted to avoid using something that we are just from calculating. In as much as I know it is correct and I know it will be okay, but it's just a habit that I'd want you guys to get. When you're performing these calculations, in most cases, there's a high chance that maybe you made a mistake at some point. So why risk it? In a case where you have an option of using something which is given in the question, that is point A, or using something that you're just from calculating, that is point B, I would rather you use something which is given in the question because you've got no doubt in whether it is okay or not. Because imagine if you made just a tiny, tiny error in your calculation for your answer in to find the velocity at B. It will mean that it will affect this value here, meaning that it will affect the velocity at C altogether. That mistake will be carried forward. Have you got why I avoided this in the first place, Regan?
Yes, sir, I understand. But if I'm confident, I can still do the same.
Yeah. And like the way I'm confident that this answer is correct, I can still use this and I'll find the correct answers too.
All right, thank you, sir.
Yeah. Okay, so this is how you approach a question like this one. Any other questions before we proceed? So in the previous example, we looked at a case where we use the conservation of energy when we are only dealing with conservative forces. But now we have an example where a non-conservative force is present. And what is a non-conservative force? Perhaps we have to start by answering that question. Because if you look at the question here, they are actually asking us to find friction, how large an average frictional force opposes the motion. So the fact that we are looking for friction, it means that friction is present. And if friction is present, friction is an example of a non-conservative force. So here we're saying that that expression for the conservation of energy for PE initial plus KE initial is equals to PE final plus KE final. This will not just do it anymore. Or the one is that P change in PE plus change in KE is equals to 0. This becomes incorrect if something like friction is present. Why is it like that? And what really is a non-conservative force? Well, non-conservative forces are forces whose work done depends on the path taken. An example is friction. The work done by friction depends on the path you take. If you decide to move, let's say 5 meters like this, and then 5 meters down, and then 3 meters this side, how much work you would do depends on the path you take. If you take a longer route, you do more work. So non-conservative forces by definition are forces whose work done depends on the route that you take. But if you look at a force like gravitational force, if you look at something like gravitational force, of course, I mean the weight. If you look at the work done by the weight, when it comes to the work done by the weight, if an object starts from the top here, and this object gets to move from the stop point, and it takes this route, sliding on an inclined plane until when it hits the ground. Let's say this is 5 meters. And in another case, let's say this just falls straight downwards until when it hits the ground. Let's say this is 4 meters here. When it comes to the work done by the weight, it turns out that the weight would do the same amount of work, whether it slides down like this or whether the box just falls vertically downwards. The work done by this box, by the weight of the box, will still be the same. Do you guys agree with that? Do you guys agree? Would you want me to prove that this is actually true? Okay, so Nzila wants us to prove. Okay, so before I get to proving, gravitational force is a good example of a conservative force. Frictional force is a good example of a non-conservative force. Gravitational force is a good example of a conservative force. So again, non-conservative forces are forces whose work done depends on the path taken. They do more work when you take a longer path. They do less work when you take a shorter path. But conservative forces do not care what route you take. If you take a longer route or you take a shorter route, the work you do will still be the same. Consider this example where you have an object of mass, let's give it a mass, let's say mass 10 kgs. This box is to be, let's say it's to move from point A to the ground. Or I can even say it's moving from here, from the bottom. Yeah, it doesn't matter. Let me just start from here. It's going to slide from point A to point B. All I'm looking at here is it's changing from a height at A somewhere there. It's changing from that height, that's the height at A, and it's coming to a height at the ground, which is a height at B. Let's take the first route, sliding on the inclined plane. Let's take this route first. If it's going to slide down the inclined plane, what will be the work done by the weight? Well, let's position our box somewhere here. If you were to position the box somewhere here, the weight, you know to say the weight will always act vertically downwards. The weight will always act vertically downwards. But if you remember from our discussion, I think under forces, the weight will have a component that will be pointing along the line of the inclined plane. It will have a component which will be going like this. And the component of the weight, okay, so the weight will have a component that will be pointing down the inclined plane. And you guys should remember that this component was given by mg and it was sine theta, where theta was the angle at the bottom here. So I haven't given what this theta is. You can easily find it, of course. So let's see how it goes. If the box is to slide down, then the weight that is actually doing work is going to be this piece of the weight. That's the one that is doing the work there. Because remember, I said for work to be done, it's the force times the distance moved in the direction of the force. The force which is in that direction, that 5 meter direction, it's this component. So this component is the one doing the work. So in this case, work done by the weight will actually be equals to the mg sine theta multiplying that 5 meters. But what is this mg sine theta? Well, sine here, opposite over hypotenuse. So sine theta will be opposite over hypotenuse. The opposite is 4. So this will be 4. The hypotenuse is 5. So sine will be equals to 4 over 5. So I can now get my mass is 10. My g is 9.8. Where there is sine theta, I'll just put 4 over 5, because that's what sine theta is. So I'll have 4 over 5 here, then times 5. If you see this expression reduces to just 10 times 9.8 times 5 and 5. This is just times 4. And if you do the math here, you should see that if you calculate this, what do we get? 9.8 by 4, then by 10. We get 392. This is work done, so I can say joules. This is the work done if we take this route. Now the question is, what if we take the direct route of just falling downwards? Well, if we were just falling downwards, what is happening? Well, now we see that the force that is doing the work, it's not even a component. It's the full force now. It's the mg. Mg is the weight. And we know this is 10 by 9.8. And this will just be 98. So I can say the weight or the force doing the work is actually 98 newtons. Through what distance? The distance is this one, which is 4 meters. So now the force, 98, the distance, 4 meters. So the work done in that line becomes the force, 98, not 9.8, 98. The distance, 4. And again, if you multiply 4 by 98, what you get? You see that in this approach again, you used to get the work done as 392 joules. What am I driving at? Weight or the gravitational force is a non-conservative. It's a conservative force, sorry. Gravitational force is a conservative force. The work done by a conservative force does not depend on the path. Regardless of the path you take, the work that will be done by that force will still be the same. We have just demonstrated this using the gravitational force. For an object that, if it slides down like this, we've seen that the weight will get to do work, and the work will be 392 joules. And even if it was to fall down to this level, to reach this level, it will still do the same amount of work. So this is what we mean when we say conservative forces, the work they do does not depend on the path we take. Okay, any questions up to there? Okay, now that we've described what conservative forces are and what non-conservative forces are, what do they actually do? to our system? What do they change? And how do we modify the conservation of energy to actually get to account for non-conservative forces? Well, think about non-conservative forces as a leakage in our system, something which is stealing energy in our system. We're not really destroying energy per se. We're not really destroying energy or anything, but they just steal energy, or energy is being lost. They are means which cause energy to be lost by a system. So what happens? Well, picture this. A good example I'd give you is whenever a machine is working, or whenever something falls, you always get things like sound or maybe heat and so on. That energy which is being given out as heat, it's actually lost energy. A good example that I'll give you is let's see, what would be the best example? What would be the best example here? So many examples in my mind, but I'm trying to see the best one that I can give you. Okay, there are really so many, but among them, you can even think about trying to see the easiest one, really. Okay. I'm not really getting any easy ones. Most of them tend to be a little bit complicated. When you're trying to do something, let me give you an example of a laptop. Even a laptop is okay. A laptop is a machine trying to do, a barber machine. Yeah, that works as well. So even when you look at a barber machine, the goal is to vibrate so that it cuts hair. That's the goal. But it doesn't just do that. In trying to do its work, it ends up giving out heat as well. And apart from heat, it also gives out sound. Why? Why does it do all that? Or those two, the sound and the heat, they are also forms of energy. So instead of just doing its work, vibrate and perform a task, it ends up losing or resulting into other forms of energy that we might not really have use for at that particular time. So that energy which is coming out as heat, that energy which is coming out as sound, it is actually lost energy. Now, in our scenario, we look at an object that is falling from some height. So this object is falling from some height, and then it falls all the way up to the ground. What happens is that this object, not all its potential energy actually gets to be converted. Part of it will be lost. You guys will actually agree with one thing. I know you guys, at one point or so, you've watched cartoons before. And what you agree with me here is when something is falling in air, as it is falling in cartoons, they'll actually exaggerate it a little bit, but it's something that actually happens. When something is falling in air, it tends to produce some form of sound. It might not be a very large sound, but that sound will actually be there. There'll be some sound which will be produced. In cartoons, this sound will actually be a lot for you to notice. Now, that sound, where is it coming from? Because this object is just falling. So where is the sound coming from? Sometimes that sound comes as if it's a whistle or something. It's not like the object will be whistling while falling, but that sound will come out. Now, that same sound, it's actually some form of energy being lost by the system. So in this case, if non-conservative forces are present, because it's the non-conservative forces that lead to energy being lost. So now we say that if you get the energy you had initially, potential, and the potential energy you have by the time you end whatever this process is, get the kinetic energy that you had initially and the kinetic energy after the process takes place. Now, if non-conservative forces are present, we're saying that when you look at how energy has changed, the change in energy, let's say the change in potential energy, and also look at the change in kinetic energy. Now we're saying that these two will no longer be equals to zero. They'll no longer be equals to zero. Why? Because there has been some change. Some energy has been lost. In fact, this concept now says that whatever the difference will be, whatever the change will be, whatever that change will be, it will actually be equals to the energy lost due to non-conservative forces. So whatever the difference is, we know this is supposed to be equals to 0, but if non-conservative forces are present, then they will not be equals to 0. So, but whatever they will give us, that will be equal to the work done or the energy lost due to non-conservative forces. So in most cases, the non-conservative force that will be present will be friction. So we can say that PE plus change in KE will be equals to the work done against friction, or the work done against friction. That's a bit better. The work done against friction. In most cases, that work will have a negative sign since friction steals. So in some cases, you find a minus put there, but here I'm using the fact that it's the work done against friction, so I am not putting that negative there. I'm just writing it like that. But it's okay if you put a negative there as well. Because in most cases, when you perform this calculation, you find that you have a deficit, a negative here. So that negative will literally have to account for this negative which is here. Okay, so, and how do you calculate the work done by friction? Well, friction is a force. Like all forces, it has to do work. So the work done by friction will also be equal to the force by the distance. So it will be the force of friction multiplying the distance through which friction was acting. This is how we calculate the work done by friction. So in this way, we observe that the conservation of energy now has been modified to account for the energy that is lost when non-conservative forces are present. So this is the work done against that non-conservative force. Let's see an example. The question that I introduced when we were just starting this part. This question here. We see an object, this is a bit, that has to slide from here through point B and to it reaches point C. We're taught to say that here a non-conservative force is present. We're trying to find how large that non-conservative force is. Well, the first thing here is to actually use the conservation of energy. Because if the non-conservative force is not present, we know it's supposed to be equals to 0. But if it is present, then the difference will be equals to the work done against that non-conservative force. So the first step is, let me get the question. The first step is to evaluate the change in PE plus the change in KE. I want to see what this will be equal to. Read what you said. Which part again?
The part where you said we will equate it to 0 is a non-conservative force is present. Didn't get that.
No, I was saying that we know that this is supposed to be equals to 0 if a non-conservative force is not present. But because we know the non-conservative force is present, when we get this part, it will not be equals to 0. You get that? Huh?
Oh, all right, sir.
Yeah. So if a non-conservative force was present, we know this will not be 0. But if a non-conservative force is not present, then this will be equals to 0. So this is what we're looking for. So the first thing I want to do is I want to evaluate the left-hand side here. So I want to find the change in PE. Notice that now I'm not using that PE initial equals to PE initial plus KE initial. Just actually calculating the changes themselves. So let me get change in PE. Change in PE will be equals to PE final minus PE initial. So this will be mg PE final. This is at C. They want me to get how large the frictional force opposed the bead as this object went all the way up to point C. So it's from A to C. So it's at C minus mgh at the start point at A. So if I do the math here, do I know the mass of the bead? 15 grams. 15 grams represents 0.015. 1, 2, 3, yes, no. 1, 2, 3, so not this. This is 1, 5, 1, 2, 3, yeah. This is what 15 grams is in kgs. So I know to say this is going to be 0.015 by 9.8. The height at C. The height at C is 50 centimeters. This becomes 0.5 in meters minus the height at A. So that's the mass, 0.015 by 9.8. The height at A is here, 80 centimeters. So 80 centimeters in meters, that is 0.8. So let's do the math here. What are we getting? So we have 0.015, or I can just say 0.5 minus 0.8, then multiply this by 0.015 by 9.8. You guys verify this. Are you getting this? We go through this again. That's too big though. I think we'll get something a little bit smaller. That's 0.015 by 9.8 by 0.8. Okay, yeah, not this. I think you're getting something like negative 0.0441. This is what you're getting, right? Yeah. So next up, we get the change in KE. This is going to be KE final minus KE initial. So this is half mv at C squared minus half mv at A squared. So let's see, this is half. I can pull out the half. The mass also is 0.015, so that I only have this at C squared minus V at A squared. So I've pulled out these two because they are common. I've just factored them out, and I've left that difference there, so that my multiplication is a little bit easier. So let me see. Are the velocities given? Let's go into the question. The question says it has a speed of 2 meters per second at A, and it reaches and it stops when it reaches point C. Since it stops at C, then the velocity at C is 0. So the velocity at C is actually 0. So that part is going to be 0 there, meaning that we actually only have half times 0.015 times negative, this is going to be 2 squared. 2 squared, that is just 4. So this is negative 4. Don't get mistaken. This minus is not being squared. It's just the 2 which is being squared there. So let's see what we get. We have, that's just going to be 2 by 0.015, which is 0.03. So this becomes the change in KE. You guys can verify that too. So when we use change in PE plus change in KE, we see that change in PE, we had minus 0.0, that was 441. Change in KE, we've also just seen that this is going to be 0.03. We observe that these two will not give us 0. Instead, when we combine them, we get minus 0.0741. So this is not 0. It's close to 0, yes, but it's not 0. What the conservation of energy here tells us that in this case, because friction is present, the sum here will be equals to the work needed to overcome friction, to overcome that non-conservative force. So this is actually equal to the work done by force of friction. And how do you calculate the work done by force of friction? Well, it's the force of friction multiplying the distance through which that force of friction was applied. The force of friction throughout the slide, it was acting along the direction of motion because we know it opposes motion. So when the direction was changing, the direction of the friction was also changing. So throughout, the direction of the friction was along the direction of motion. Maybe not necessarily in the same direction, maybe a little bit opposite. What am I trying to say here? I'm trying to say here is the distance is actually the full length here, the full length of this wire. And the full length was given here, 250 centimeters. This would just be the same as 2.5 in meters. So that becomes the length and our distance. So we now have 0.07441 being equal to the force of friction multiplying that 2.5. So that the force of friction will be equals to minus 0.0741 divided by 2.5. Okay, so let's see what we have. 0.0741 divided by 741 divided by 2.5. Okay, so what are we getting there? We get negative 0.02964 newtons. This is the frictional force that opposed the motion. Now, our answer here is minus. When you look at the answer that they have here, it's a positive value. Why? Because the question is not asking for direction. The question is only asking for how large a frictional force opposed the motion. So our value is negative to mean that the distance was something like this. This is the distance. Frictional force at each point was in the opposite direction. So that is why that comes out as a minus there. But if you wanted to make sure it's a positive, then you were supposed to observe that throughout work done by friction, the frictional force will be in the opposite direction to the displacement. You could have put a minus here, which would have made this a positive, but not necessary. You can conclude that therefore, the frictional force that was actually acting on this object was 0.0296 newtons. Okay, so this is how you deal with the conservation of energy when non-conservative forces are present. In the next session, we'll look at the concept of power, and after that, we're going to continue looking at more questions that have to do with work, energy, and power generally. So feel free to share the questions as you find them. You guys will be happy to help you guys through, and invite your friends as well. Let everyone benefit, provided they're able to join us. Now, guys, have a good night.